Good afternoon, everyone. My name is Marissa Beedham, and I am an OWWA staff member, and I will be moderating today's session. If you are collecting CEUs, please be sure to enable pop-ups in your browser and then complete the pop-up survey when it appears during each session. If you have questions for any of our presenters, please use the Q&A feature that's featured on the right-hand side of your screen, and we will address them after the presentation, time permitting. I would like to thank all of our speakers for participating today. In recognition of their contribution, the OWWA will be making a donation to Feed Ontario, an organization that supports local food banks in Ontario. And with that, I would like to introduce our first speaker, Helen Louis. Helen works as a scientist at the Walkerton Clean Water Centre. She has 6 years of research and training experience in the water treatment industry. Helen's main responsibilities at the centre have been conducting pilot testing projects and delivering training courses. Welcome, Helen.
Sorry, I was muted. Thank you, Marissa, for the nice introduction. Good afternoon, everyone, and welcome to the section. And so I'd like to introduce our pilot testing experience with some Ontario First Nation communities. And the topic today is to reducing chlorinated disinfection byproducts in drinking water. So before I started with our project experiences, I would like to introduce our pilot testing services. So at the center, we provide pilot testing services to all of our clients to provide information about water quality characteristics, performance of their treatment systems, and also whether there's an opportunity to optimize it. And also we can test alternative treatment options. Our pilot testing topics include, but not limited to, control of natural organic matter, disinfection byproducts, iron manganese control, arsenic removal, cyanobacterial cyanotoxin controls, and also coagulation optimization. So first of all, what are TCHMs and HAAs? There are trial methods and then halostatic methods. There are many species in each group. Right now in Ontario and also the federal government in Canada, we only have 4 of the TCHMs and 5 HAAs are regulated, which are listed here, but there are definitely more species in each group. So far, our regulation in Ontario and also Health Canada is 100 microgram per liter as running annual average of the quarterly results. So that means we measure THM every 3 months, and we average the 4 most latest 4 results to get the average value for THM results of the running the RAA value. So that means if we if we have one value that's over 100, but the overall average is actually lower than 100, it means there's not an adverse. So the same way, the HAA also regulated as 80. So how do THM and HAA formed? Whenever we dose chlorine to our water, the chlorine can react with natural organic matter or NOM and create THM and HAAs. So chlorine is like very wild use. We use it for primary and secondary disinfection. We also use it for like zippo muscle controls when we dose it to our raw water. And sometimes we use it to regenerate our grain sand media for iron manganese control. So whenever we dose chlorine water, there's a chance of forming THM HAAs. And the formation of THM HAAs depend on chlorine concentration, chemical makeup of NOM and their concentrations, contact time between chlorine and NOM, and also the temperature. So if we look at the list of them, the easiest way to get lower THM HAA is to remove NOM from our drinking water. So NOM is usually quantitatively measured by dissolved organic carbon, or DUC, We also measure it by UV absorbance at 254 nanometer wavelengths. So the difference between the UVA or UV 254 and DUC is UVA only measures the aromatic portion of natural organic matter from water. So it's like aromatic portion of DUC. That's then we come up with this kind of way of evaluating the proportion or like components of the of natural organic matter, which is we divide UVA by DUC, called SUVA or specific UV absorbance. SUVA indicates the characteristics of the norm. When we have SUVA higher than 4, that means norm is mainly humic or hydrophobic. So it has higher DBP formation potential and chlorine demand. If SUVA is between 2 to 4, means norm we have in water is a mixture of hydrophobic and hydrophilic. It has medium DBP formation potential and chlorine demand. So when we have less than 2 of SUVA, that means it has lower disinfection byproducts formation potential and chlorine demand. So I'm going to share 2 of our previous experience on how we reduce T-Sham and HAs by removing NOM from water. The first one is the Binomial First Nation. So this First Nation located about 5 kilometers north of Thunder Bay is a flying town, or we can access by by winter roads. It has about 300 residents, uses lake water, surface water, as a water source. By looking at the characteristics of raw water, it has relatively high levels of DUC. So that means it has high potential to form DBPs. And when we calculate their SUVA value, it's about 4. So that means it has high potential to form DBP, has high chlorine demand, but it also means we can use enhanced coagulation to remove NOM from water. But it also has low turbidity and low alkalinity, which makes it hard to form flocks for conventional treatment. That's during this project this is the Benchskill jar test study. So right now the community is on a boil water advisory since 2013. And the plan right now to get rid of the boil water advisory, the community wants to retrofit the CARI system with enhanced coagulation followed by either conventional or dissolved air flotation. So they want us to test which clarification process works better for their community. So we had the community ship water to the center, and then we test with 2 different jar test technologies and then compare with the 2 clarification process. So our project scope was to investigate if enhanced coagulation is sufficient to remove NOM under cold water conditions. And the second is to compare the performance of 2 clarification processes, conventional cementation versus dissolved air flotation or DAF under cold water conditions. So what's the difference between DAF and conventional? On the left-hand side of the picture on the left-hand side is our DAF jar tester. So the clarification process is like after flocks has been formed in the water, we pump microbial from the bottom of the tank, and then all of the flocks will form a blanket on the top, and the clear water will be sampled from the bottom of the tank. So that means no flocks will be settled. Compared to the conventional cementation, all of the flocks will be settled at the bottom, clear water on the top. So that's the difference of those 2 technologies. And the main advantage of DAF compared to the conventional cementation is it has shorter start time and has shorter flocculation time. And it's not as sensitive to low temperature. So that might be a bonus for this project. But again, we tested both technologies. During the test, we kept our water cool through the test. we control the temperature to be around 2 to 6 degrees C. However, at the community, the temperature could be even lower in winter. Okay. So for each type of jar testing experiment, 4 coagulants were, we selected 4 different coagulant products. ALS is also aluminum sulfate. It's also called alum. It's the most commonly used coagulant in the industry, and also it's more affordable. But then it will consume a lot of alkalinity, and they're going to drop pH a lot, which in this case, alkalinity is very important to keep the pH stable, and then it's important for the disinfection process. So if we use alum, that means we may need to boost alkalinity up eventually. And also alum doesn't work quite well in a low temperature. So we also choose another 3 coagulant products that are improved with cold water performance and a less pH adjustment, less need for pH adjustment, and less alkalinity changes. So this is a table showing our jar test conditions. You can notice that the conventional on the left-hand side of the column is the conventional cementation. On the right-hand side is the DAF jar testing set conditions. You notice that they're set up slightly differently because we want to optimize the performance of each treatment technology and then compare their performance. That's why the conventional cementation has longer second stage flocculation and clarification time. Okay, so this is a sum of results about NOM, or natural organic matter removal. For each figure, we have 2 y-axes. On the left is the DOC readings, on the right is the UV absorbance readings, and the blue line shows the ratings of the conventional cementation results, and the orange line for DAF. And then the squares for DUC, triangle marker shows the results of UVA. So from here, I could tell, like, by comparing the 2 clarification processes, conventional cementation and DAF performed very similarly. So we didn't see the better performance of DAF in cold water in this case. So they perform very similarly, and all of the coagulant also perform similarly. They all have their optimal dosage at around 60 milligrams per liter. However, I have to note that the ALS, or alum, which is the figure number 2, or figure B, has dropped pH to somewhere below 6.5 and use up almost all of the alkalinity from water. So that may be an important factor to consider for this project. And also for the samples with highest DOC removal, we conduct another Benchskill test called simulated disinfection system test. So we took that clarified water and a dose with certain amount of chlorine and kept in dark at room temperature for a certain period of time. Afterwards, we sample for THM and HA values to see how much THM and HA were formed during that period of time. So in this case, we chose, we dose chlorine at 7 milligrams per liter, which is a relatively higher, high dose. The reason why we want to choose that is, like, we know their DOC level was a little high to start with, and also we want to get the highest formation potential to get the maximum formation of TCHM. That's why we dose a little higher. However, chlorine residual after the whole test was much lower than 2. So that means we could also drop the TCHM, drop the chlorine dose afterwards. But this is just giving us the worst case scenario. And they also chose 2 detention time for the SDS test, which were 3 and 5 days. So right now, the community is saying their average detention time in the distribution system was about 3 days. However, we want to test if we extend it for another period of time to represent the worst case scenario. We chose 5 days as another detention time. So in here, we can tell that if we compare the 2 clarification processes, the conventional cementation process performed better, like had a lower TCHM and HEA values in most of the cases than DAF. And also the TCHM HEA formation increased over time. So the TCHM HEA values are higher in 5 days, after 5 days than the 3 days. And also all of the HEA values we got were higher than the MAC value, unfortunately. But as I said just now, this is the indication of a worst case scenario. And also what we did is we dosed chlorine to the clarified water instead of a filtered water. So if the community wants to use, have another filter after, say, a GEC filter after the enhanced coagulation process, they could further reduce DUC and reduce their TCHM HEA levels. So this is really just a worst case scenario. Okay, so far that's the Binomial project. And we also did another pilot testing project with Chipos of Nawash unceded First Nation. This community, located at southwest coast of Georgian Bay, they have about like 800 residents. They use Georgian Bay water as their water source. Their raw water has low DOC, low turbidity, but they're also on boil water advisory. So right now they're trying to retrofit their existing plant and get a new plant. So far, they're using coagulation, inline flocculation, followed by pressure filter, followed by cartridge filter, UV disinfection, and chlorination. That's their current treatment. However, they're going to get a new plant, and they expect to have a membrane system for this, because when we look at the DOC, when we look at their SUVA value of their natural organic matter, it's less than 2. So that means coagulation may not be effective to remove DOC from water. So like they're trying to use another design. And then the new design will be with a membrane system. And they're also thinking about GEC and inline coagulation. So our project scope was to investigate the performance of TCHM and HA from 2 treatment options. The first option will be membrane followed by GEC filtration. The second will be if we add inline coagulation to the first train, see whether that will help removal of TCHM and HAs. So this is our pilot plant design. So we tracked water from, we're located very close to the community. So we tracked their water from the source from Georgian Bay and loaded the water to our outdoor storage tank at the center. We pumped the water through a static mixer going through our ultrafiltration or membrane. And then the membrane filtered water stored temporarily in an indoor storage tank before going into a GC pressure filter. So during the test, the membrane has nominal pore size about 0.2 micrometer, And then effluent flow rate was about 9.3 gallons per minute. Transmembrane pressure was negative 1.4 psi. And per minute cycle was 30 to 60 minutes in between back pause. And then the GEC GEC pressure filter was filled with 0.75 cubic feet of virgin coal-based carbon, and flow rate was about 3 gallons per minute, with active back contact time was around 2 minutes. And that's the first train. And for another test, we added inline coagulation. So that means we dose coagulant before the statin mixer, before ultrafiltration. And then the product we used was PAC-6, which is a polyaluminum chloride coagulant at a dose of 5 milligrams per liter. So by looking at our results, the lighter blue bar represents the GEC DOC removal from GEC, and the darker one represents DOC removal from ultrafiltration or from the membrane. So if we look at the two bars, looks like majority of the DOC or natural matter removed by GEC. And then inline coagulation further reduced the GEC, slightly reduced the DOC from water. Oops, sorry. And then we'll also collect our water from ultrafiltered effluent and the GEC effluent. And then we did another SDS test, or simulated disinfection system test. This time we chose 2 chlorine doses and 3 contact times. So that's the reason why we chose 3 contact times, because right now the community has a lot of leaks in their distribution system. Their next step is to fix all those leaks, and they expect to have longer detention time in their distribution system eventually. Right now, they expect the detention time after fixing their whole system will go up to around 8 days. But right now, the average time is about 6 days. So that's why we're covering a bigger range of detention time. So if we compare the TCHAM and HA results from the 2 trains, definitely GEC reduced a lot of TCHAM and HA from the ultrafilter effluent. So that makes sense because GEC reduced most of the DOC from water. And also the inline, by comparing, say, figure A and B, by comparing those 2, the inline coagulation slightly improved the TCHAM removal for the whole train. So similar case for HAAs. All of the TCHAM HAAs are below the MAC values, and the HAAs are further removed by GEC. Okay. So some conclusions. Overall, TCHAM and HA levels can be effectively reduced by lowering natural organic matter concentration prior to chlorination. So for the Binomial First Nation project, they enhanced coagulation followed by the conventional or DAF, conventional cementation or DAF, removed over 50% of DOC. So they effectively reduced TCHAM and HA levels. However, then because we have a high DOC level to start with, they may want to consider some other barriers to add to the system to further reduce their TCHAM and HA levels. In terms of a Chief of Snailwash City First Nation project, the ultrafiltration followed by GEC filtration significantly reduced DOC, and that kept the TCHAM HA level below half of the MAC. the inline coagulations likely promote the reduction of NOM and DBPs. So I would like to thank all of our partners, and thanks to their cooperation and suggestions and guidance. And here's some references. Here's our disclaimer. If you're interested to any of our pilot testing results, most of our pilot testing reports are posted on Drinking Water Resource Library. You can visit their library by drinkingwaterresourcelibrary.ca or going to our main website, wcwc.ca, and then you have access to the library directly right there. Okay, I'd like to thank everyone's attention today. Any questions?
Great, thanks very much, Helen. So I don't see any questions coming in yet, so we'll just give it a few moments. We do have some time, so if anyone does have any questions, please feel free to submit it into the chat box just to the right of the screen there. Okay, so that must be a sign of a great presentation. I don't see any questions coming in right now. So I'd like to thank Helen once again for presenting and everyone for joining us today. We will be getting our next session promptly at 1:30. Thanks, everyone.
Thank you.